Hi, everyone. My name is Nathan Pacini. I am a marketing manager from Data Science Dojo. Uh, and today I have Neil Leiser here with me, and he is going to be giving a presentation on an introduction to convolutional neural networks with TensorFlow. And this will include a little tutorial at the end. I might refer to it as part two at the end here. But Neil is a data scientist at Iwaka, which is a fintech startup, and he's also the host of the AI Stories podcast, where he brings on data professionals and tech leaders, and they talk about their careers and how they use AI in day-to-day life to impact our world. So with that, Neil, why don't you go ahead and things should be good to go.
Yeah, thanks. Thanks a lot for the intro. Can you all see my screen? Is that good?
Yes, we can.
Okay, perfect. So yeah, hi everyone. Today I will give you an introduction to convolutional neural networks with TensorFlow. I really wanted to thank Data Science Dojo for organizing this event, and yeah, hope you will find this useful and interesting. So just a few words about me first. I don't think you know me quite well. So as you can hear, I'm not from the UK. I was born and raised in Belgium, but I moved to London 7 years ago to study civil engineering at Imperial College. And then in 2019, I kind of realized that I was really interested in data science and machine learning. So I did a master in London, and there at the end of my master, I did a research thesis on predicting the output of solar panels with satellite images. And this is where I kind of went deep into convolutional neural networks because I had to deal with images. And so that's also how I got interested in this topic. And that's why I'm giving this talk today. As mentioned already, I'm a data scientist at Iwaka, which is a fintech startup. And there I build machine learning algorithms for credit risk. So we are a lending company. We lend money to businesses. And so we have algorithms which will decide who we are accepting for a loan, how much money we are offering, also some tools for losses prediction. So this is what I'm working on. And in my spare time, I also host the AI Stories podcast, where I invite people from all around the world to talk about their career and how they use AI in their day-to-day. Season 1 is now over, and season 2 will start again in September, October. So if you're interested, feel free to follow. All right, so let's start with the talk now. Just a brief overview of what I want to talk about. I'm first going to give a brief introduction, like 5 minutes, on AI and neural networks, just to bring everyone on the same page. Then we're going to go through the theory behind convolutional neural network. And again, this is just to show you the intuition behind how they actually work. And finally, we'll have the collab, where I will show you how you can build your own CNN algorithm with Python and TensorFlow. So hope you will find this useful and interesting. Let's start with the intro. So in 2012, you may or may not know, but there is this AlexNet paper, which is very famous. And this is where deep learning becomes well known to everyone. And the AlexNet paper basically sets a new record on the ImageNet challenge. And ImageNet, so you have a picture here, you don't see things very well, but it's just an image classification problem. You have loads of images, I think 1,000 different classes, and you need to classify the images correctly. And so you can see that on the graph at the bottom, like in 2010 and 2011, the best algorithms had an error rate of 28 or 26%. But in 2012, suddenly, with this new AlexNet deep learning algorithm, the error decreases to 16%. And that's like a big boom, a big impressive thing in the world of AI. And lots of researchers from computer vision who were doing non-deep learning research actually moved to deep learning because people kind of realized that deep learning is very powerful and could actually be the future of computer vision. So there is actually a paper from 1985 which trains a neural network using backpropagation. And convolutional neural networks have been around since the 1990s. So how come that it's just in 2012 that we realize that neural networks, and especially CNNs, can actually be so powerful? I think there are two reasons for that. The first one is we actually need a lot of computing power to train a neural network, and this wasn't really available or known at the time. And the second reason is we actually need a lot of data. And the AlexNet paper showed that with a lot of compute power and a lot of data, you can actually train a neural network. Nowadays, it feels easy to train a CNN, but back at the time, it was much more difficult. So because I don't know how familiar you are and what's your background, I'm just going to give a brief intro on neural networks before moving to convolutional neural networks, because neural networks is really the basics. And neural networks is essentially a network of neurons. So each dot here, each circle is a neurons, and it's inspired by the brain. And all those neurons are kind of connected to each other by arrows, and each arrow represents a different weight. So neural networks have three different parts. They have the input layer, right, which is the input data. There is the output layer, which is the prediction, essentially. And in between that, you've got the hidden layers. Here we've got two hidden layers of 4 neurons each, but actually you can have 10 hidden layers, 20 hidden layers with how many neurons you want. There isn't really any rule for that. This is just a toy example. And yeah, each arrow is a different weight. So here we've got 3 times 4, so we've got 12 weights in this layer. Here we've got 16 weights, and here we've got 4 weights, so 22 weights in total. And using backpropagation, you can train this neural network and find what the optimum sets of weights are. I'm not going to go into backpropagation or deep into neural networks. If you're interested, there are lots of readings on that. I will provide some references at the end, but hopefully you get some idea of what is a neural network and how it works. And yeah, I believe we're going to do questions at the end, but or do we want to, I see we have a question now or a hand. But yeah, let's leave the questions at the end of the first part, because I might answer some questions, yeah, in the coming slides. So yeah, that's how neural networks works, and CNN are actually parts. Well, you will see neural networks within CNNs. So let's move to the interesting part of the talk, convolutional neural networks. And the first thing that we can see, so I described before, CNNs were used for image classification, right, with the ImageNet paper. And an image is actually just a matrix, right? It's a matrix with, and each value within this matrix is a pixel or a number. So here you can see it's just a 28 by 28 matrix. And so the question is, why do we want a neural network? Like, why do we actually need, why do we need a CNN, and why not just a neural net of the first part? So why not using just a neural network instead of a convolutional neural network, right? An image is just a matrix. So what you can do is flatten this matrix into a vector, and you can then feed this input into a neural network, right? And that's it, that's done. Why don't we do that? Well, first of all, as a human, let's say you want to classify dogs and cats. How do you do? You're going to look actually at groups of pixels, right? You're going to look at eyes, at ears, at the color of the skin. And that's exactly what CNNs do. They take spatial dependencies into account, and they look at groups of pixels. Neural network will only look at individual pixels, and that's very difficult. If you just have like a vector of pixels and need to identify dogs and cats, the task will be much more difficult, even just for a human. So that's the first reason why we use CNNs. And the second reason is that they are actually more efficient to process images. So here you have some kind of toy example of a CNN. The input is an image, and then the network, the algorithm, is divided into two parts. The first part, which is in blue, is the CNN. So we have convolutional layers and then pooling layers. And the second part, after the flattened layer, is just a neural network. And so the neural network is going to take the features from the CNN and use those features to make the classification. But the CNN is going to extract the useful features from the images. And so we've got convolution and pooling layers, and I'm going to talk about this in more details in the next slides. But for the moment, just keep in mind that we've got a first part, which is convolution and pooling layers, and a second part, which is a neural network that hopefully you're kind of familiar with. So the intuition behind neural networks is that behind CNN, is that on the first few layers of the model, the CNN will be able to capture tiny details within the image, like edges, for example. And as you get deeper and deeper into the model, the algorithm manages to extract more kind of human interpretable features like eyes, heads, flowers. And so basically the first part of the network looks at details, and the last part looks at higher level features in some sense. So let's dive into convolutions. Here you have a very clear example of what a convolution actually is. And there is a note here, a comprehensive guide to CNNs. I really recommend you to read this. I'm taking a lot of images from there. And yeah, it's very good. If you want to have a good understanding of CNNs, really recommend reading this blog post. So convolution. Here we have a 5x5 image, which is represented in green, right, with some pixel values, which are zeros and ones. And the convolution is actually a kernel. So it's this 3x3 yellow square, which goes around the image. That's a kernel, and that's the process of doing convolution. You can see the red numbers on the image, the ×1 or ×0s. Those are the weights of the kernel. So those are the weights that the neural network need to learn in order to extract meaningful features from the image. And so by kind of rotating this kernel around the image, we get what we call this convolved feature, which is this kind of pink box. And so the first value, for example, the 4 here, is obtained by multiplying this kernel by the values on this top left corner. So here we've got 1 × 1, here we've got 1 × 0, here we've got 1 × 1, 0, 1, 0, 0, 0, 1. So in total, we've got 4 ones and 5 zeros. And so that's why you get a 4 here. You repeat that and you get the convolved feature. So that's it. That's what a convolution is just a kernel which rotates around the image to extract meaningful information. Now, you can again see a kernel here. And I want to describe 2 additional words which are quite important: stride and padding. So the stride is by how much you should shift the kernel. So you can define the strides as you want. Here, in this case, the stride is 2, because you can see that the kernel shifts by 2 squares on the right and by 2 squares from top to bottom. So the stride is 2. The second thing that's important is padding. So you can see here those dotted lines, which kind of upsample the image. That's what we call padding. So here we've got horizontal and vertical padding of 1, because we're adding one square on each side of the image. And the reason for padding is that sometimes you have interesting features on the corners of the image. And if you don't actually use padding, the kernel might be missing those features that are just close to the edges. And by using padding, you can actually capture better information sometimes. Finally, I discussed the pooling. So if you remember here, we have a convolution. So we apply the kernel to the image. And here I'm just showing a single kernel, but I don't see any reason why you cannot apply 10, 20, or 32 kernels to this image, right? You will just have 32 different convol features. And that's what we do in practice. So that's why here you can see 24 by 24 by n1 is just n1 kernels that we've applied to the image. And that's why you have kind of different images here, or convol features. After the convolution, it is quite common practice to apply this pooling operation. And all this pooling operation does is it reduces the size of the convol feature. That's it. So here you can see it's 24 by 24 by n1. After the pooling operation, the dimensions here are 12 by 12 by n1. So we reduce the dimensions by half. How does this pooling operation works? You have different kinds of pooling. You have max pooling or average pooling. Max pooling is probably the most well-known technique and the one that works usually quite well. And essentially here, again, you just have a kernel that rotates around this image or this convol feature. And max pooling is very simple. All it does is it takes the maximum from a set of pixels or values. So here you've got 4 values. If you apply the max pooling, it takes the maximum, which is 20, and extracts the 20 here. We use a stride of 2 here. So if we move the kernel 2 squares on the right, we have another max pooling, and here the highest value is 30, and that's how we get this 30 number here. Average pooling is similar, but instead of taking the max, we just take the average. And we use pooling to reduce the dimension of the image. It makes it much easier to process the image, but it also helps to reduce overfitting because it's actually robust to rotations and translations. So a short example, let's say that you have an eye in this feature, in this square. And let's say that suddenly you're rotating this eye. You will rotate the values within this square. But if you apply the max pooling, the largest value will still be 20. And so the max pooling will still extract the feature, even though you've rotated or translated the picture. And so it makes the CNN kind of robust to rotations and translations. And that's basically it, actually. You have your input, you apply a set of kernels, convolutions, you have this max pooling layer, you can have another convolution followed by another max pooling operation. Here we've got 2 convolution, but you can have 10, 20, there is no rule for that. And then after that, you can just flatten the output and feed everything to the neural network, which will then do the job for you. So that's, hopefully that gives you some kind of intuition about how neural networks work. And if it's still not clear, hopefully it will be much clearer with part 2, where we're going to build our own algorithm using Python and TensorFlow. But first, I believe we have some time for questions about the theory, and then we can go into the code.
So I'm seeing one question, and this is from Nahal, and they want to know if you can share, you have a source, the Comprehensive Guide to CNNs. Can you share that link with everyone? I know we'll share the slides with everyone with the recording, and so you'll be able to access it through there. But are we able to share that source now?
So here I've got a few sources here. Should I just share the slides on the chat since I'm done with the presentation?
Maybe, yeah. And then Data Science Dojo team, if you can share the Google Colab with everyone now, that'd also be time to do it. Sophia, I know you have your hand raised. If you can ask your question in the chat, or not in the chat, but in the Q&A tab, I'd appreciate it. And then Neil, whenever you're ready, I have a second question for you.
Yeah, so I've shared the slides and the references are at the end. But yeah, I'm ready for the second question.
Okay. So this is from Mauricio. So they're referring to a second step, I'm guessing in the neural network, but why does it have so many layers in the second step?
Can we clarify the question? Which second step exactly? Is it the one from?
I am not exactly sure. Let's wait for clarification. I think, Mauricio, I think you're on one of our live streams, but if you can just clarify for us which second step
neural network here? Is it the neural network from this CNN that you're talking about? Or yeah, which second step is it? And then I would be able to answer.
And then Sophia has a question that I think will be a lot easier to answer right now is, how do you determine the kernel?
So the size of the kernel, that's a good question. So here, for example, we've got a 3x3 kernel that rotates around the image. And the size of the kernel is actually a hyperparameter. So we don't know what a right size actually is. We need to try different things and see what works, which is usually how it works for neural networks. Typical sizes are 3x3, 5x5, 7x7. So you should try a bunch of those, see what works, but there isn't a clear rule on what kernel works best. If you have a very small image, I would recommend trying smaller kernels. If you have a large image, just try bigger kernels. That's usually how it works.
Okay, and then this one is from Brent, and they would like to know how to create the convolved feature. They had a hard time following.
So if I just recap here, you have the kernel and you have some weights, right? The ×1, ×0, ×1. Those are weights that the neural network will learn. Here is just examples of zeros and ones, but in real life, it's not like that. It's just values that the neural network would learn. And then you just rotate this kernel around the image. So you see, every time you rotate the kernel, you get a value here on this convolve feature. How do you get that value? By multiplying the weights from the kernel, so the zeros and ones that are written in red, by the pixel values in the image. So to again describe the example that I shared here, you would do 1 × 1, right? Because that's the first weight of the kernel, plus 1 × 0, which is 0, plus 1 × 1, which is a 1. So we have a value of 2 at the moment, plus 0 × 0, which is 0, plus 1 × 1, plus 1 × 0, plus 0 × 1, plus 0 × 0, plus 1 × 1. So in the end, we've got 4 ones. If we sum all of them together, we get the value of 4. And we repeat that by shifting the kernel around the image to get this convolved feature. Hopefully that's clearer.
Perfect. And then James, I want you to know, I see your question. We're going to wait to answer that one at the end, because I think that one's going to take a little longer to answer. Should be good to go on that. So let's answer one more question just before we start the demo. And I want to go back to, where is he or she? Mauricio. So the question about the layers in the second step, they are saying yes from the image in the slide. I think it was the one that you showed.
Yeah, I see. So the intuition here, actually you can have as many layers as you want. Basically, the convolutional neural networks extracts the meaningful features from the image. So for example, if you want to classify, if you want to detect whether someone has a face, there is a face in the image or not, the CNN will kind of, yeah, I know, sorry, I haven't shared my screen, but there is nothing to really show. I'm going to move to the collab after. Or maybe I can, well, yeah. So the first part of the CNN is basically extracting meaningful features from the data. And those features could be eyes, mouth, color of the skin, hairs, things like that. But then you still need a neural network to kind of, well, detect all the kind of find patterns within all those features. So the CNN will find all the interesting features, but you still want the neural network to see, okay, if the person has a mouth, long hairs, and eyes, then it's a girl. If it has short hairs, eyes, and a mouth, it's a boy. So it's kind of, the neural network still has to find patterns within those features, but the CNN will find the interesting features. And so the job of the neural network is much easier because the CNN does all the hard job of finding the interesting features. So yeah.
Perfect. Okay, and then
let's go. Let's start with the collab. So hopefully now you've got some understanding of how CNNs actually work. So let's see how we can build one. And again, the collab is divided into two parts, a very short intro to TensorFlow. You will see it's very simple, very similar to NumPy. So if you know NumPy, it's just going to be very similar. And then I will show you how you can train your own CNN using the fashion MNIST datasets. So if we go through the code, first I'm just installing TensorFlow and importing a bunch of libraries, nothing that's interesting. I import TensorFlow and TensorFlow.keras. Keras is a library built on top of TensorFlow, which makes it very easy to build neural networks. So I'm just going to use that for the tutorial. And here we've just got a bunch of basically cells which show you how TensorFlow works. And TensorFlow, the main idea behind TensorFlow is this tensor, which is very similar to a NumPy array. So here I create a tensor which is essentially a matrix of size 2 by 3. And if you kind of then print this variable to the screen, you can see how it looks like, but it's basically very similar to NumPy. Like NumPy, you can create an array of ones. If you call tf.ones, you specify the shape, you get an array of ones. And like NumPy, you can do some operations between the matrices. So here we've got two matrices. You can multiply, add them together. You can do an element-wise multiplication. You can do a matrix-matrix multiplication. All of this you don't need to know for the tutorial, but it's just some recap and just to explain to you that TensorFlow is very similar to NumPy, but we use this to train neural networks because it works very well, it's computationally efficient, and it's built specially for that. So that's why we're using tensors instead of NumPy. And like NumPy, you can also manipulate the matrices. So here, for example, I create a variable 1, which has a shape of 2 by 3. And then I reshape this variable to have a shape of 1 by 6. So 1 row and 6 columns. And you can see that it worked. I get another tensor. And also, again, like NumPy, you can concatenate different matrices on top of each other. Well, you can have, yeah, basically here, I build this variable 1 and I concatenate it on top of each other. So you get the same matrix twice, basically. So the first dimension, the number of rows is increased from 2 to 4. But again, this is just play around with it if you're interested. It's nothing that you need to know for today. But yeah, just found it interesting to show how you can use tensors and manipulate tensors. So that's the first part, hopefully very easy, and yeah, just play around with it in your free time. The second part is the fun bit, which is CNNs with the fashion MNIST dataset. So let's go slowly through this code. The first thing is just load the data. There is this command using keras, which loads the fashion MNIST dataset. And I have training data, training label, test data, and test label. And then here, I'm just storing the names of the class. So it's an image classification problem, and we have 10 different classes. You can see we've got t-shirt, trouser, pullover, dress, coat, sandal. You can see it's different kinds of clothes, which is why we have the name fashion MNIST. Here, just some visualization. So you can see that the training data, we've got 60,000 images of size 28 by 28. The labels, we just have 60,000 labels, which is the class. And then the test data, we have 10,000 images of size 28 by 28. So hopefully here, very simple. Here, I have some codes which you don't need to understand. It's just to show you what the data set actually looks like. So you can kind of visualize the data set. We've got 16 images here. You can see it's just different clothes. The images are 28 by 28, so the quality isn't great, but hopefully you can see that's a sandal, that's a sandal, that's a sandal, that's a pullover, sandal again, shirt, ankle boots, bags, well, different kind of clothes. So a classic machine learning image classification problem. Once we've loaded the data, the next thing to do is to actually process the data. And the processing is very, very simple and only needs 3 steps. The first step is that I divide the data by 255. And that's just because all the values in the images are between 0 and 255, and I want values between 0 and 1. So just divide everything by 255. That's just very common practice. And then the second thing that I'm doing is that I'm expanding the dimension of my training data. And the reason for that, so you can see here, I print, remember that before, sorry, this should probably go in front. But basically, I'm expanding the dimension of the training data. And I will talk about this in a few seconds. The third thing that I do is that I'm just splitting my training set. Remember, we had 60,000 images in my training set, and I'm splitting it into training sets and validation sets. So that I don't touch the test set, I only look at the test sets at the end of the process. I train my neural network on the training set, and I leave the validation set to see how well my algorithm is performing. So here, if you look at the shape of the training set, it's now 50,000 rows, right? Because I removed the validation set. We have 28 by 28 images. And then we have this extra dimension here, which is just a 1. And this is what I've done here. I just expanded a final dimension, and it is a 1. And the reason why I'm doing this is because the CNN will expect to get an input of this shape. And so if you don't expand the dimension, the CNN is just not going to work. And that's because usually with more complex images, you have actually 3, the dimension here is 3, because you've got 3 different channels for blue, red, and green colors. So here it's simple, it's just a 1, but that's why I'm doing this step here. So processing is very simple. We've processed the data, and now the final thing we need to do is to build the network. So this is where I build my convolutional neural network. And it might look quite complex at the beginning, but we're going to slowly go through that, and you will see it's actually very, very simple. So the model is, I create this tfk.sequential object, and this is just a list well, it takes as input a list of layers. So each line of code here is going to be a layer from my convolutional neural network. So each line is just a different layer. So this algorithm is divided into 5 parts. The first part is the input layer. That's simple. You just need to specify the shape of the data that you're going to feed into this algorithm, right? Your model should know that it's going to be images of size 28 by 28 by 1. So that's what I'm doing here, and we've specified the input layer. Then, if we just look at the comments and not at the code, we've got the first, the second, and the third convolutional layer followed by the max pooling layer. So that's exactly what I described on the slides. We've got a convolutional layer followed by a pooling layer. Finally, at the end, we have a neural network. So that's just a classic neural network, first with 256 neurons, and then with 10 neurons at the end, because we have 10 classes. And so each neuron is going to show, at the end, is going to show the probability that the image belongs to a class. We take the maximum probability, and this maximum probability is going to be the class that's the prediction class, essentially. So if we go into the convolutional layers in more details, the 3 layers here are exactly the same or very, very similar. And all it does is, first of all, you have the convolutional layer, which is the tfkey.layers.conv2d. And so those are just kernels which are going to extract information from your image, as I showed in the slides. 32 refers to the number of kernels that we will apply to the image. So in the example, we just applied 1 kernel with zeros and ones, remember? Here, we're going to apply 32 different kernels to extract more information from the image. The size of the kernel is going to be 3 by 3, as I showed you before, and that's because the image has a kind of small dimension. We set the strides to 1, which means that we move the kernel by 1 square. And we have this activation function, which makes the CNN nonlinear. If you're interested in activation functions, there is lots of literature on that. I'm not going to go into too much details here. And then all you do here is have the pooling layer of size 2 by 2, which just reduces the dimension of the convol feature by 2. It divided by 2. And that's it. You do that again with the second layer, except that here we want 64 convol feature instead of 32. And then you do that again with the third convolutional layer. So we have 3 layers here. In the end, we feed this into the neural network, and finally, we get the prediction. So hopefully that's quite simple. All you need is an input layer, a bunch of convolutional layers, and with max pooling, and then finally the neural network. And that's it. That's your model. Here there is some reading on the softmax activation function that I'm using at the end of the network. If you're interested to learn why I'm using this activation function, then there is a very good resource here with some formula, but I'm not going to go into too much details. So remember what we've done, and yeah, don't look at the maths here. You also don't really need it. All we've done is we've loaded the data, we've processed the data, and we've defined the model. We just need one last thing before we can train the model, and it's this cell here. We need to define an optimizer, which this optimizer will help us to find the weights of the suitable weights for the algorithms. And we use Adam, which is very, very standard. We need a metric, and the metric will tell us whether the algorithm is performing well or not. And so here we use a sparse categorical accuracy, which is very standard for when you use classification. It essentially gives a value of 1 if you've classified the image correctly, and a value of 0 if you didn't. And then we also want a loss function, because accuracy is not differentiable. So we want a loss function to train the neural network. And so here we use the sparse categorical cross entropy. And again, there is some reference here if you want to know why. But I would say this is not really particular to CNNs. That's just a classic deep learning approach. You need an optimizer, a matrix, and a loss function. So read about that if you're interested. What you do after that, if you compile your model, you set you set the optimizer, the loss function, and the metric, and then all you need to do is train the model. So here I'm calling model.fit. I'm fitting it to the training set. You obviously need the labels because the model is learning, and I'm using this validation data because I want to see how my model is performing on unseen data to avoid overfitting. Here, I've already trained the model. It doesn't take too long using Google Colab if you use GPU, but I've trained it already. And you can see here the loss function. And basically, as we train the model, we want the training loss to decrease, right? Because we want the loss to be as small as possible. And we want the validation loss to decrease as well. So this tells me that, okay, my model is learning, the loss is decreasing. Let's now see how our model performs on the test set. With this line of code, I'm just evaluating my model on the test set that we've never seen before. It evaluates, and we can see that the accuracy is around 89%, which means that 89% of the time, the model will classify the images correctly. If you want to play around with the code, you can probably improve this by quite a lot. You will just need to maybe add additional layers to the model or change the kernel size or change the activation functions. You can play around with the model, add more layers if you want. But if you want to learn, I will encourage you to try to beat this 89% score on the test set. I'm sure you can improve on what I've done. Here we can kind of see the prediction. So again, this is the data set, and you can see on top, you can see the prediction, and at the bottom, you can see the label. So we can see that the model is doing quite well. For most of the values here, the prediction matches the label, right? Sandal, sandal, t-shirt, t-shirt, trouser, trouser, bag, bag. So it looks like the model is doing quite well. And we can also see, don't worry about this code, but we can see where the model fails, actually. So here you can see examples where the model fails. And you can see that it's mostly around t-shirts, pullover, coat. That's where the model seems to struggle. Because here it predicts coat when it's a dress. Here it predicts a t-shirt when it's actually a shirt. And we can see that it's actually quite difficult here. Here it's a pullover. It predicts a pullover, but it's actually a coat. So anyway, you can see where the model is wrong. And if you want, you can also print the confusion matrix to see where your model struggled the most and try to improve it. But yeah, this just shows that we've basically trained a convolutional neural network on the MNIST dataset, and the model seems to perform quite well with like an 89% accuracy on the test set. Yeah, feel free to try to beat this and improve on that during your free time. And yeah, I'm going to take some questions now. Hope this was clear.
Okay, perfect. So we do have 16 questions and probably counting. So Neil, I know yesterday we talked that we might go a little bit over time. Is that still okay with you if we go a couple minutes over?
Yeah, I'm happy to stay 10, 15 minutes longer to answer questions if people are still okay with.
Okay, perfect. So let's try and get, and I've been kind of going through these as you've been talking, and I want to try and get the longest question out of the way first, and I'm hoping you're the best person to answer. And so one, I would suggest opening the Q&A, read it yourself. I'm going to read it out loud, but it's about a paragraph. So I'm going to read it out loud while you read it. So this is from James. Is there a way to align CNNs with digital twin simulations while updating real-time data Python pipeline? I'm currently using Unreal Engine and Unity in creating dynamic immersive VR digital twins while connecting them with CNN optimizers for real-time data input. Would you understand which optimizer would work best? Also, what is the optimal number of epochs one should use to maximize the accuracy of the CNN?
Cool. So first of all, I'm not very familiar with digital twin simulations, so not sure if I will
I'm
be.
I'm a twin. I actually have a twin brother. I am also not familiar with digital twins.
Okay, so even if you're a twin and you're not familiar, that's but yeah, basically, but I still think I can probably help with which optimizer would work best. Adam is quite, well, the classic one, I would say. I pretty much always use Adam because it's known to be quite good. There might be better optimizers for CNN. I'm not a specialist, but I know Adam is pretty good. It deals with momentum and things like that. So I would recommend Adam, although if it doesn't work, do some research. I'm sure you can find better ones as well. And the second question, which is, what is the optimum number of epochs one should use to maximize the accuracy on the CNN? So I cannot give you one number because it just depends on the problem, but you can see here. So here I've only used 10 epochs just because I didn't want to train the CNN for too long. Usually we would use more epochs, but at some point, so the validation loss here is decreasing, but at some point you will see that you will actually start to overfit. And what overfitting means is that the training loss will go down because you will learn better and better on your training sets, but the validation loss will start to go up. And so what I recommend doing is looking at that. And when you see that your validation loss starts to go up after, I don't know, 10 epochs or so, you can stop training your model because it means that your model is overfitting and won't be as good. So that's how you can find the right number of epochs, I would say. And that's called early stopping. If you're interested, yeah, just look at early stopping.
And I saw James had a second question a little later on, so I'm going to ask that now as well. So in this tutorial, are you using the softmax optimizer as a result of having 10 different class outputs?
So softmax, I'm basically using the softmax activation function in the end. And so it's not really an optimizer, it's an activation function, which, so basically my network is, you're going to have 10 neurons at the end of the network. And what the softmax does is it transforms those values into kind of probability. So you're going to have 10 probabilities, which is the probability that your image belongs to a class. So the first neuron would be the probability that it belongs to the first class. The second neuron would be the probability that your image belongs to the second class, etc. And then you can just take the highest probability, right, to have the prediction. So that's what the softmax does. So I'm using the softmax as the final layer, as the activation function of the final layer of the CNN and the neural net, basically.
Okay. And then this one's from Paula. How do you determine the size of padding?
So again, that's the same as kernel size. I would say that's a hyperparameter. So here you can see there is no padding. I didn't use any padding at all. I think that's the default in Keras. So I didn't specify any padding here. But basically the size of the kernel, the size of the padding, the size of the stride, all those things, you need to try different things and see what works. Here, no padding works well. Sometimes you can use 1 or 2 paddings. I haven't seen much more than 1 or 2, except if you're really expecting to have a lot of information. I mean, it could be also higher, but if you don't expect to have a lot of information close to the corners, yeah, I think 0, 1, or 2 to start with should be all right. Yeah, you just need to experiment. There is no strict rule here.
All right. And this is from Pedro. What's the main difference between max pooling and average pooling on performance?
So usually max pooling performs better. And that's because max pooling extracts the dominant feature. It takes the maximum value, so the highest activation in some sense, and it extracts this, whereas average pooling does some kind of smoothing. So that's why I think max pooling is often better, but I don't think there is a strict rule. Like, it could be that sometimes average pooling works best, but from my experience, yeah, I pretty much always use max pooling. It's kind of the standard because it extracts this dominant feature, I believe, whereas average smooths things out. But yeah.
All right. And this one's from Anushia. How many images approximately do we need for performing CNNs? I know it's subjective, but is there like some type of guideline, or if you can provide some type of idea, that would be great.
Very good question. And yeah, I'm not really sure. I will try to help and say that, first of all, it depends on the difficulty of the problem. If you have, like, if you just want to classify black and white images of numbers, for example, that's probably easier than if you want to classify very complex, large images of, I don't know, different types of dogs, right? So it depends on the complexity of the problem. And it also depends on the number of classes that you have. If you have 2 different classes, you need much less images than if you have 1,000 classes, right? Because you want enough samples from each class. I would say probably a couple of thousands of example for each class. That would be my guess. So if you have 10 classes, at least 10,000 examples. But again, it depends on the complexity of the problem, and yeah, on the complexity of the problem, the size of the images and things like that.
Mm-hmm.
But yeah, a couple of thousands at least.
All right. And this is from Naomi. Is it possible that using too many convolutional layers could degrade the classification accuracy?
I think it could be possible, but yeah, I'm not. It will probably depends what you're doing, I guess. If you add additional layers with the wrong activation functions and things like that, I guess it can. You just need to try. It also, I would say, depends on the problem. Sometimes fewer layers might work better. It's not like all the time increasing the size of the model is better, but you will see now that all those state-of-the-art algorithms are very, very big. And so usually would think that by increasing the size of the layer, we will get a better performance. But then, yeah, if you want to have a very, very big algorithm, you're probably going to need lots of computing power. You're going to need to wait a long time to train your model. And so it might not be as good. So but I think, yes, it could be possible that adding more makes the performance worse, but usually more weights means better performance.
Okay. And sorry, I'm just filtering out questions as they get asked. And so this one's from Zach. Do you need to optimize the hyperparameters? What would you use? Something like grid search CV?
Yeah, exactly. You could use that, some kind of grid search. Yeah, a grid search with different sets of hyperparameters like kernel size, number of layers if you want, the number of channels, right, of kernels that you're going to have in each layer. Yeah, you can use some kind of grid search to find the best parameters, or yeah, that's usually good practice And yeah, remember that you would also need to look at the learning rate, the batch size, all of these, which are more common deep learning algorithms, would also help. And I'm pretty sure there are other methods than grid search that you could use for kind of smarter searches, but which might be better. But grid search is exactly something that you could do.
Okay. And then this is from Murad. Can we use CNN with other types of data, such as genetic data? I mean, we can classify numeric values, not only images or CNN will not work properly. So do we have to use images in a CNN, or can we use other types of data?
You can use other types of data. I'm sure there is some research on language. There is probably some research on language for CNNs, but they really work best and they are well known for images. So if you have like tabular data, I would not recommend to use CNNs at all, because traditional algorithms like XGBoost or even regression and random forest will perform much better. So yeah, don't use CNNs on raw data and images, and on text. There might be some research, but I don't think there might be one or two a few papers where they've been useful, but it's really not the standard. Like CNNs are well known for images, and except if you really have a good reason, I would just use them for images or visual data, because that's what they've been built for.
Okay. And then this one is from Roya. Sometimes TensorFlow takes a lot of time to be run. Is there any way we can decide better from the beginning how many layers to use?
So one trick that I have is, and I'm going to go back to this graph. You can see here that the training loss is going down. And forget the validation loss. You can see that the training loss is going down. So when you start, make sure that that's the case. Like train a big enough CNN such that the training loss is going down, because this means that your algorithm can at least learn the training data. And once this is done, you can have some techniques to avoid overfitting, like dropouts, stronger regularization, things like that. But first, make sure that your training loss is going down by the amount that you want, because I see sometimes people training a neural network and it doesn't work. That's because if your model isn't big enough and cannot even learn the training set, it's never going to do well on the validation or on the test set. So first of all, make sure that your training loss is going down, and then you can start looking at your validation loss and reduce overfitting. So there isn't a clear size, but just make sure your model is big enough to be able to learn from the training data. Because if you can't overfit your training data, then your model will never be able to do well on the test set. That would be my advice.
Okay, so we're gonna try and get through like 2 or 3 more questions before we sign off. So this is from Kumar. How do we decide the initial weights used in the filter?
That's all random. There is some initialization that you can set. I'm not sure what's the default one, but it's basically Keras does this for you, and it's pretty much random. There might be some smarter ways. I'm not an expert in that. There might be some smarter ways to initialize the weight, but random should be fine. And then by training your model, the weight will converge to their optimum value. But initially, you don't need to worry about anything. You just set a random value, and by looking at examples of, or this is a dog, or this is a cat, or this is a dog, or this is a cat, and using backpropagation, your model will learn by itself what the weights should be. So here, I believe it's just initializing things pretty much at random, because obviously your model doesn't know what the task is going to be. It doesn't know that it's going to be used to classify clauses. So in the beginning, just initialize things at random and let the backpropagation algorithm and the neural network do the job.
Mhm. Okay, so I think this one's going to be our final question, and we're going back to Roya. Can CNN use a combination of image pixel array and some other related variables from Excel? For instance, merge MRI pixel array plus patient demographics from Excel. If so, can you please explain how? Thanks.
Patient demographics. So I assume that the first one is an image and the second one is raw data.
I would assume. Yep.
And so, yes, you can actually do that. And what you would do is you would have the CNN, you would train the CNN on the image data only, because you don't want to train the CNN on the raw data. But then you remember that in the end, you flatten the features from your CNN and you feed that into a neural network, right? So here, I don't see any reason why you cannot just add additional neurons in the input layer, which will be your demographic data. So the CNN should only be trained on the image, but at the stage of the neural network, instead of feeding it only the input from the CNN, you can also feed additional input. So it's at the second step of the algorithm that I would feed those additional features, basically.
Okay, perfect. And I am going to cut questions off there because we are 10 minutes over, and I want to make sure we have time to do a closeout. So thank you, Neil. I'm just going to share my screen really quick so we can talk about next week's webinar. Give me 1 second, everyone. So next week will be July 27th, so 7 days from today. And we're going a little earlier than we were today as well. This will be happening at 9:30 a.m. Pacific on July 27th. We're going to have a crash course on designing a dashboard in Tableau. And we'll have Irene Diomi with us. She's a data analyst as well as a Tableau ambassador. So we're going to be talking about what is Tableau, how do we design a basic dashboard, how do we include a bar chart in our dashboard, and as well as other things, and how are we going to format it for good design practice. So if you want to learn some quick things on Tableau, join us next week along with Irene, and we'll see you all there. But Neil, thank you so much for being here with us today. We really appreciate it. We'll make sure to get the recording of this up. It'll be up on our YouTube channel, as well as on our website, online.datasciencedojo.com. Also, if you are one of our subscribers to our newsletters, or if you RSVP'd on our website specifically for this event, we'll make sure to send you an email with the link to the recording and the slides and the Google Colab and all the good things Neil shared today. So Neil, we really appreciate you being here. Everyone, thank you for joining, and I hope everyone has a good rest of their day.
Thanks. Thank you. Thank you very much.